The question that I have is, could you discuss the critical state concept of sand with respect to direct shear testing? So here we're going to talk about the fundamentals of the stress-strain behavior of sand with respect to loading that it experiences in a direct shear test. We are going to discuss things like under what circumstances sands exhibit strain softening, volume expansion, volume compaction, things like that. We already know a little bit about the direct shear test itself, right? So it's performed in a box called direct shear box, and the box has two halves, the bottom half and the top half. You fill the box with sand and pull the top half horizontally with respect to the bottom half until failure. So you are basically forcing failure to take place on this horizontal plane. Of course, before you apply, you have a normal stress applied to the sample. Since sands don't show any cohesion, in principle, you need just one test in order to evaluate the friction angle. But typically, we'll do a couple of tests so that you can average it out, accounting for experimental errors. But it turns out, compared to materials like steel or aluminum, the behavior of soil is a little bit more complicated. So we need to understand the basics a little bit so that we can represent its behavior in design analysis properly. Before we go on, let me define these parameters. So here we have the vertical load P and the vertical displacement delta N. From P, we can calculate the vertical stress simply by dividing P by the cross-sectional area of the direct shear specimen, which will be the cross-sectional area right here. From delta N, I can calculate the normal strain by this equation, where little h is the height of the specimen. In the horizontal direction, T is the shear force, delta S is the horizontal displacement. From these two quantities, we can calculate the shear stress and the shear strain by these two equations respectively. Like we did before, if I take a little element right here, the stresses acting on that element are shown over here. If I were to plot the data we obtained during the test, my plots might look something like this. In the first graph, I'm plotting the relationship between the shear stress and the shear strain, and in the second graph, I'm plotting the relationship between the void ratio E and the shear strain. It turns out that what I'm showing here are typical of dense sands. Dense sands exhibit strain softening like this. As per the variation of the void ratio, it turns out there's always a little bit of compaction initially, and then the sample tends to dilate. That means void ratio increases, and eventually, at very large shear strains, the void ratio becomes a constant. It reaches what we call a critical void ratio. On the other hand, if the specimen had been initially loose, then the relationships would be similar to what is shown here in red. In the shear stress shear strain space, the specimen will show simply a typical hardening behavior, and then the void ratio will continue to decrease. But here is the complication. The definition of dense and loose doesn't necessarily depend only on the void ratio. It turns out that it depends on the combination of the void ratio and the normal stress sigma n. Here are some typical relationships corresponding to different values of normal stresses and initial void ratios. Specifically, I have data from 4 different tests plotted here. Test 1, Test 2, Test 3, Test 4. And similarly over here, this curve corresponds to Test 1, this corresponds to Test 2, this to Test 3, and this to Test 4. Test 1 and 2 are conducted with a normal stress of 50 kilopascal. Test 3 and 4 are conducted with a normal stress of 100 kilopascal. The initial void ratio of the specimens used in test 1 and 3 is 1.2, whereas the initial void ratio of the specimens used in test 2 and 4 is 0.5. Let's compare the behaviors of test 1 and 2 first. Both of these tests were conducted with the same normal stress, 50 kilopascal, whereas one had a higher initial void ratio and the other one had a lower initial void ratio. So what do we get? The one with the lower initial void ratio behaves like a dense specimen. The one with the higher initial void ratio behaves like a loose specimen. So what else do we see? Two things. Number one, they both reach the same ultimate failure stress. So tau u1 equals tau u2. That's number one. Number two, both of them reach the same final void ratio, which is what we call the critical void ratio, right? So the critical void ratio is the same. So at least from these two tests, we see that the critical void ratio is uniquely tied to the normal stress, regardless of where they started from. So this one started from a void ratio 1.2, but this one started from a void ratio 0.5. But regardless of those initial values, they both reach the same final value, final critical void ratio. It turns out that is because they both had the same normal stress of 50 kilopascal. Now we will see that this pattern is confirmed by the results of the other two tests, test 3 and test 4. These two tests had the same normal stress of 100 kilopascal. They both reach the same ultimate failure stress. They both reach the same critical void ratio 0.6. Again, this void ratio 0.6 is uniquely tied to the normal stress of 100 kilopascal. Let's make one more observation here. So here I have listed the sigma n values and the corresponding critical void ratios. For 50 we have 0.8, for 100 we have 0.6, right? So from these two we see that the critical void ratio decreases with increasing sigma n. Let's just focus on this relationship first. Here is the relationship. I repeated these also just for convenience. So basically, it's been experimentally established for sand there is a unique relationship between the critical void ratio and the normal stress. And that relationship looks like this. By the way, this was done long time ago by Casagrande. This relationship serves as the basis for defining what a dense specimen is and what a loose specimen is. So this is what happens. If the initial point plots in this region, that is the region below the critical void ratio curve, then the specimen is going to behave like a dense specimen. And similarly, if the initial state, meaning the combination of the void ratio and the normal stress, plots in this region above the critical state line, then that particular specimen is going to behave like a loose specimen. What do we mean by like a dense specimen? Well, dense specimen shows strain softening. Dense specimen shows a little compaction in the beginning and then dilation. And similarly, a loose specimen shows a continued hardening behavior, no strain softening. And similarly, in the void ratio versus gamma space, a loose specimen shows a continued compaction. There's no dilation. Let's see if the four specimens whose behavior we have shown here conforms to this principle. Test 1 had a normal stress of 50 and an initial void ratio of 1.2, right? So the initial point plots right here, and therefore it plots in the loose range, and it does behave like a loose specimen, right? Test 2 had the same normal stress, 50, but the initial void ratio is 0.5, and therefore it plots right here. it plots in the dense range, right, below the critical state line, and therefore it's supposed to behave like a dense specimen, and it did behave like a dense specimen. And I have marked the other two specimens as well. T3 is supposed to be a loose specimen, and it does behave like a loose specimen. T4 is supposed to be a dense specimen, and it does behave like a dense specimen. Strain softening here, and a little compaction and then dilation. So the other point that I want to emphasize here is that regardless of where they start, they always end up on the critical void ratio relationship. So for test number 1, it starts here, but it always travels on that vertical line because in a direct shear test, we don't change the normal stress, right? So we keep 50 kilopascal initially, and it stays as 50 throughout the test. And therefore, the path from the initial point to the final point is this vertical line right there, but it starts there and ends up on the critical state line. All right, so the initial void ratio is 1.2, the final void ratio is 0.8, because that point happens to be right on the critical void ratio line. Similarly for T2, it starts here and it travels like this, ends up over there. T3 starts here, travels like this, ends up over here. T4 starts here, travels vertically up, ends up over here. So if I tell you that the initial height of the specimen used in test number 1 is 2 inches, and ask you what the height of the specimen would be at failure, what would you say? So this is what I would do. We know the initial void ratio, we know the final void ratio, and therefore we know the change in void ratio, which is 1.2 minus 0.8, right? So we know the change in void ratio, we know the initial height, and therefore we can find the change in height using the proportionality rule that we have used a number of times so far, which is this right here, right? So this is the phase diagram. So using the proportionality rule, I get a change in height of 0.36, and therefore the final height of the specimen should be 1.64 inches. The final point that I want to make here is the following. Here we made a couple of very important observations concerning the fundamental behavior of sand. First, we found that there is a unique relationship between the critical void ratio and the normal stress. Then we saw that if the initial state plots in the region below the critical void ratio line, the specimen will behave like a dense specimen, and if it plots above the critical void ratio line, the specimen will behave like a loose specimen, right? And we know exactly what that means over here, right? These ideas are collectively known as the critical state concept. This concept was originally proposed by Casagrande, but later further researched and systematically popularized by a group of researchers from the Cambridge University, namely Professors Roscoe and Schofield. This concept now forms the basis for interpreting test data and also the soil behavior in general. It also forms the backbone of most constitutive models that we have around, which are basically the mathematical models relating stresses to strains. These mathematical models are a crucial part of conducting a finite element analysis of the soil behavior or soil structure interaction behavior. Now let's talk about the other observation we made, which has to do with the failure stresses, right? I put some numbers here just so we have some physical feel for these things. What did we find in the first place? Well, just as the critical void ratios are uniquely related to the normal stresses, the ultimate failure stresses are uniquely related to the normal stresses. So when we have 50 kilopascal, regardless of the initial void ratio, the ultimate stresses are the same. And similarly, when we have 100 kilopascal, regardless of the initial void ratios, and therefore the initial parts of the stress strain curves, the ultimate failure stresses are still the same. So here it's 40, here is 80, right? So I listed those numbers over here. So I plotted these numbers in the tau versus sigma space and defined my Mohr-Coulomb failure line. The Mohr-Coulomb failure line obviously has to also pass through zero because we are talking about sand here, right? And that line obviously has to pass through these 2 points also. But sometimes it may not pass through all of those points, then you have to run an average line. But in this case, they do, and I get a friction angle of 38.7 degrees. We call this friction angle as ultimate friction angle and the failure line as ultimate failure line because the failure line was constructed using the ultimate failure stresses, right? These ultimate failure stresses are also called the ultimate shear strengths. Now let's focus on the peak points over here. Both test number 2 and test number 4 had the same initial void ratio 0.5. Test number 2 gave us a peak stress of 60. Test number 4 gave us a peak stress of 120. I listed those here. Now using these numbers, I can define another failure line, and this failure line is called the peak failure line. The corresponding friction angle is called the peak friction angle. So here we get a value of 50.2 degrees. Is the peak going to be very different from the ultimate friction angle? We know the value of the initial void ratio for both of these tests is 0.5, right? So it turns out that the difference between phi peak and phi u depends on how different this initial void ratio from the critical void ratio. But the critical void ratio depends on the initial confining pressure, right? And therefore the difference between phi peak and phi u is going to be a combination of the initial void ratio and the normal stress. For instance, if the initial void ratios for these specimens had been say 0.55 or something like that, we might have had a line somewhere in between. The further discussion is a little bit more involved and beyond the scope here. So what we need to know here is that phi u is a unique property of the soil. On the other hand, phi peak depends on the initial state. It depends on the initial void ratio and also the confining pressure that you apply on the sample. So I have made a remark over here.